Today we also want to talk about two important subspaces. We're going to start with an M by N matrix. So A is an M by N matrix. One important subspace that we want to talk about is the column space. The column space of A is the span of the columns of A. The notation for this, because this is math and we always have to have an abbreviation. Sometimes we don't put parentheses around the A, but I don't have italics to separate the A from the column space part, so I'll put the A in parentheses. So the column space of A, denoted column space of A, is the span of the columns of A. This has to be a subspace because we know that the span of a set of vectors is always a subspace. The column space of A is a subspace of Rm. A also gives us another important subspace. The null space of A is the solution set to AX equals 0, denoted null A. The null space of A is a solution set to AX equals 0. We know that AX equals 0 must contain the 0 vector. So AX equals 0 is always consistent. And when we write the general solution, we'll have a bunch of vectors defined by any free variables that are available. The null space of A is a subspace of Rn. The null space of A comes from all the x's. So those are the x's are in Rn, but the span of the columns of A are in Rm because the columns of A are in Rm. So here are two important subspaces. The column space of A is the span of the columns of A. That's a subspace of Rm. The null space of A is the solution set to the homogeneous equation AX equals 0, and that's a subspace of Rn. What we want to be able to do is write a basis for each of these subspaces, because that's how we're going to describe subspaces, by writing a basis. Start with a spanning set and cut it down to a basis. So there are two important subspaces defined by a matrix.